In this video, we're going to talk about how sound waves propagate through space. And just as a reminder, propagate is a vocabulary word that means move. We're trying to understand underwater acoustics, which means we need to understand how sound waves move around underwater. The first step in that is to get a picture of what a sound wave looks like. This little animation should help. You can see a sound wave moving through some medium because the wave squishes some particles together, which is referred to as compressing the particles. And that in turn creates a region of spread out particles next door. And a region that's spread out is called rarefied. The compressed particles are at high pressure and the rarefied ones are at low pressure. So particles flow into the rarefied spot, which creates a new compressed zone and a new rarefied zone further to the right. Notice that no individual particle moves all that far as a sound wave passes through. It just alternately gets squeezed close to its neighbors and then spread out. Also, the very first high pressure spot is started by some sound source vibrating and pushing on the particles. Usually that'll be a speaker for us, but in this case it's a tuning fork. There's one last piece of vocabulary that I want to tack down on this slide. We've established a couple of times that our sound wave is made of some particles being compressed together and some particles being spread out. That's actually quite different from a lot of waves that you see in nature, right? On ponds, if you see a ripple in a body of water, that's made of some particles going up and other particles going down. So in the ripple example, the displacement of the wave is not in the same direction that it's traveling. In the sound example, the displacement of the wave is in the direction it's traveling. That means sound is something called a longitudinal wave, because it squeezes in the direction of travel, while ripples are something called a transverse wave, because they displace in directions that are not the direction of travel. So on the previous slide, we showed that sound was a wave by looking at a picture of wave-like behavior, suggesting that some particles got squeezed together or compressed and some got rarefied. You can describe that exact same behavior using an equation, and I want you guys to see some patterns about those equations, even if you don't memorize all the equations on this page. The key thing I want you to take away is that this thing here is something called a wave equation, and you can identify a wave equation because it's going to have two partial derivatives in space and two partial derivatives in time. This is handy to know because once you identify a wave equation, you know that any solution to that equation is going to be a wave. And you can use your intuition from all of the waves that you've ever seen to analyze any wave equation. Now, one other detail about this wave equation is if the space derivative has a coefficient of 1, which ours does, then the coefficient in front of the time derivative is 1 over the velocity squared. So you can pick out the velocity of your wave that way. In our case, it depends on rho, which is the density of a fluid, and b, which is something called the acoustic impedance. In this case, our wave equation comes from differential conservation of momentum in a liquid, which we see described up here. This says the change in your mass flow rate with time, that's this density times velocity, has to be equal to the gradient of your pressure in space. The other equation we use to make our wave equation is differential conservation of mass, which says that changes of your mass flow rate in space have to cause increases in pressure. Rho here is the density of your medium, and B is something called the bulk modulus, which relates changes in volumes to changes in pressure. It's how hard your medium is to squeeze. Now that's nice to know, but again, I don't want you to worry too much about these differential equations or to memorize them. The main takeaways here are that sound is caused by a wave equation, which you should learn to recognize, and that we have a formula for the speed of sound, which is that velocity equals the square root of bulk modulus over density. So one tricky thing about the speed of sound, especially in the ocean, was hinted at on the last slide. Because the speed of sound depends on the density of water, it also indirectly depends on how much pressure the water is under, and also how much salt is in it. That means that the speed of sound can vary from 1484 meters per second in fresh water to about 1500 meters per second in salt water. And in fact, in the ocean, the speed of sound can vary with different depths. Now, if a wave is propagating through a medium where the speed of sound continually changes, the wave will diffract, sort of like light passing through different indices of refraction. So to summarize, sound is a wave, and in particular it's a longitudinal wave, which means that it's made of regions of compression and rarefaction. That is, particles being squeezed together or spread out along the direction of motion. It's not a transverse wave, where the motion is in a different direction than the wave's travel. Waves are created as mathematical constructs from wave equations, which we now know how to identify. They have two derivatives in space and two derivatives in time. The speed of sound in water is equal to the square root of the bulk modulus divided by the density, and we know the value of that speed of sound is between 1480 and 1500 meters per second, depending on the conditions of the water.